In last class, we have derived an important relation between the elastic constants, the diagonal tension and compression of an element subjected to pure shear or simple shear. So the equation was E is equal to 2G into 1 plus mu. Now, two more equations are there. There is a relation between E, mu and K also. So the first one is relationship between E, mu and G. Young's modulus, Poisson's ratio, and rigidity modulus. Second one is relation between Young's modulus, Poisson's ratio, and bulk modulus. So in this case, we have to consider an element like this, three-dimensional element, because it is a bulk modulus. Whenever that word bulk comes into picture, you have to take the volume of the element. So like volumetric strain, we have to compute. Change in volume, we have to compute like that. Bulk means volume. So here, I have taken an element, three-dimensional element, which is subjected to stresses in all the directions, x, y, z. So this is x direction, this is y direction, this is z direction. So you have understood that in generalized Hooke's law. So only thing is we have to take equal values of stress in all the three directions. So sigma x is sigma, sigma y is also sigma, sigma z is also sigma. So all the three values are equal. So tensile I have taken. So when all the stresses are equal, naturally the strains in all the three directions will be equal. So all are tensile stresses, sigma, and strains in all the three directions also will be equal. So I will call that as epsilon x, ex, ey, ez. They are the strains in x, y, z directions. They also will be equal. I will take that is equal to E. So all these are equal to E. Now let us apply generalized Hooke's law in x direction. So according to generalized Hooke's law in x direction, strain in x direction, Ex is given by, Ex is nothing but E here, is equal to, so I have to take the linear strain in x direction and lateral strain in y and z directions. Okay, that is the meaning. So here linear strain in x direction is sigma by E, because sigma is the stress, tensile stress given in x direction. Now taking y direction, in y direction there is a tensile stress, but in x direction it will be compressive. Therefore I have to take minus. So mu is the Poisson's ratio, because it is a lateral strain term. Mu should be taken. So stress is sigma divided by E. Next, in z direction also tensile stress is there. The effect of that will be in x direction, it is compression. Therefore minus mu times sigma is the stress in z direction divided by E. So this is the expression for the strain in x direction when all the stresses are equal. Now if you simplify this, sigma by E into 1 minus 2 mu. So I have taken sigma by E common into 1 minus 2 mu you will get. Now let us calculate volumetric strain. So volumetric strain is EV, which is the sum of all the three, Ex plus Ey plus Ez, that we have derived. So which is nothing but here E plus E, because they are all equal, it becomes 3E. So that means if you know here E as sigma by E into 1 minus 2 mu, substitute that for E here, you will be getting EV is equal to 3 sigma by E into 1 minus 2 mu. Now, by the definition of bulk modulus, how do you define bulk modulus? Bulk modulus K is defined as bulk stress divided by volumetric strain. That is sigma divided by EV. You don't worry about this one. So it is written in another form. So let us take this one. So K is equal to sigma divided by EV. We have defined it. So bulk modulus is defined as the ratio of bulk stress, that is sigma, divided by ratio of bulk stress to volumetric strain. Volumetric strain here is EV. Now substitute. Now therefore K is equal to sigma divided by EV is this 3 sigma by E into 1 minus 2 mu. So sigma gets cancelled. So E goes to numerator. E divided by 3 into 1 minus 2 mu. You will get like this. So if you cross multiply, E is equal to 3K into 1 minus 2 mu. So this is the relationship between Young's modulus and bulk modulus and Poisson's ratio. Very simple derivation. So we have to consider a three-dimensional element like this subjected to sigma equal stress, tensile stress in all the three directions, XYZ directions, and by applying generalized Hooke's law in X direction, you will be getting E is equal to sigma by into 1 minus 2 mu. Then calculate the volumetric strain, which is EV is equal to 3 times E. So substitute that value of E here. Then use the definition of bulk modulus of elasticity. K is equal to sigma by EV. You substitute for EV here and simplify. You will get E is equal to 3K into 1 minus 2 mu. Please note that here E will be in Newton per mm square. K also will be in Newton per mm square. Mu is just a constant. It is just a number. So mu is the Poisson's ratio, which is the ratio of lateral strain to linear strain. So very simple derivation. Next, the last one is relationship between EG and K. So we have derived two relations here. One is E is equal to 2G into 1 plus mu. Another one is E is equal to 3K into 1 minus 2 mu. So we have to remember these relations because a problem may be given. So where we have to find out these elastic constants. So for that you should remember the formula. All the three formula you should remember. All the three relationships. Now let us derive the relationship between EG and K. Young's modulus, rigidity modulus, and bulk modulus. So now here we are using those two equations which we have already derived. So E is equal to 2G into 1 plus mu. E is equal to 3K into 1 minus 2 mu. Now to get the relationship between these three, we have to eliminate mu here. So mu term should be eliminated. It has to be removed from these two expressions. Then we will get the equation in terms of EG and K. Now how to remove mu? So what we have to do is, so you just take the first equation. So mu is eliminated from the above equations. Take the first equation like this. You bring that mu to the LHS. So if you bring only, if you want mu in terms of E and G, it will be like this. If you simplify this, 2G mu is equal to E minus 2G. So then, therefore, mu is equal to E by 2G minus 1. This you will get. Now take the second equation. Second equation is E is equal to 3K into 1 minus 2 mu. Substitute for mu here in terms of this. So here in the place of mu, you put E divided by 2G minus 1 and try to simplify that. You will get the equation. See, very simple. The second and third derivations are very simple derivations. So you will be, if you simplify, go on simplify this. I have done it. So you will be getting an expression finally like this. E is equal to 9GK divided by G plus 3K or 3K plus G. So you have to remember so. So you have to use these three equations to find the elastic constant. If you know any two elastic constants, you can find the other two. So out of 4, E, G, K, mu, if you know any two values, you can find out the other two values by knowing these three relationships. So first derivation, second and third, all the three are important. So you have to know you should know the derivation. Now we will take up problems on that. So problems are also equally important. Using those three relationships, we can solve some problems also. So let us take one by one. When a 12 mm diameter specimen is subjected to a tensile force of 20 kilonewton, a deformation of 0.3 mm is observed over a gauge length of 150 mm and reduction in diameter is 0.0079 millimeter. Find the elastic constants. See, understand the problem here. Elastic constant means all the four we have to find out. E, G, mu, K. So when a 12 mm diameter specimen, so I have written the diagram here. So this is 12 mm diameter circular specimen rod is subjected to a tensile force or pull. It is also called as pull of 20 kilonewton. So 20 kilonewton force is applied at both the ends. So it is a tension force. When it is applied, we can see a deformation of 0.3 mm. What is the deformation? It is elongation. Because it is a tension force, this rod will elongate by 0.3 mm. When observed over a gauge length of 150 mm. That means the length of the specimen is 150 mm. So L is 150 mm. Delta L is 0.3 mm. Then initial diameter is 12 mm. So 12 mm is 0.012 meter. So everything you should be okay, 12 mm I can write. Okay, let it be in millimeter only. I don't want in meters. So it is 12 mm only we will take. So D is 12 mm. So delta L is 0.3 mm elongation, length 150 mm. Now another data he has given is reduction in diameter means delta D. So there is a decrease in diameter. Naturally, when the length increases, diameter reduces. So when elongation takes place in linear direction, reduction takes place in the lateral direction. Here lateral or transverse direction is the diameter direction. So diameter reduces. So what is the reduction in diameter? That is delta D 0.0079 mm. So this is the data given. So this is the data given. From this data, we have to compute all the four elastic constants E, G, mu and K. They are unknowns. Now first we will calculate the Young's modulus because we know the elongation, we know the force. So P is 20 kilonewton. You convert that into Newton. So 20 into 10 cube. Why? Because normally all the units, SI units will be taken in newtons and mm. So stresses will be in Newton per mm square, length will be in millimeters, area will be in millimeter square. So be careful about the units. If you have in some other units, centimeter or kilonewton, you first convert them to millimeter and Newton, then start doing the problem. Now, sigma, first we know that Young's modulus is given by stress divided by strain. So stress is sigma, strain is E or epsilon. So anything is okay. So we know that stress is force divided by area, resistance divided by area. Strain is change in length divided by original length. So P by A is stress here. Sigma is P by A. P is 20 into 10 cube. Area is pi d square by 4 for this bar. So D is 12 here, 12 mm here. So pi into 12 square by 4. If you simplify this, you get the stress as normal stress or tensile stress. So sigma is the tensile stress, 176.8 Newton per mm square. So P is in Newton, A is in millimeter square. So stress will be in Newton per mm square. Then strain, either you can write it as E or epsilon, they are same, is equal to delta L by L, change in length divided by initial length. So that those two values are given in the problem. Change in the initial, increase in length is 0.3 mm divided by L. Length of this gauge length is the length of the specimen 150 mm. So if you simplify that, you will get 2 into 10 power minus 3. So strain doesn't have any unit, it is just number. Then Young's modulus is equal to stress divided by strain, sigma divided by epsilon or E, which you are going to get 88,420 Newton per mm square. Naturally, it is not steel. So for steel, the value is 2 into 10 power 5 Newton per mm square. So that is the value for steel. It can vary from 2 to 2.1 into 10 power 5 Newton per mm square. This is not steel. Okay, it's some other material, maybe copper or brands like that. In the textbook, he has given the values of E for different materials. Anyway, you need not remember that. So for steel, you can remember. So 2 to 2.1 into 10 power 5 MPa or Newton per mm square. So the first value of elastic constant is obtained as E value like this. Next, we can calculate mu value. How do you define mu? Poisson's ratio. It is the ratio of lateral strain to linear strain. So lateral strain means epsilon lateral divided by epsilon linear or E lateral to E linear. Some books they use E, some books they use epsilon. So what I have done here is, when you are using generalized Hooke's law, I have taken the strain as E. Whereas when I am using just Hooke's law, I am taking it as epsilon. So here you can write it as epsilon. So epsilon lateral or E lateral, both are same because it is a unidimensional stress system. So stress is acting in only one direction. So we know that lateral strain is given by delta D by D. So that is in the lateral direction. Whatever change in diameter is there, divided by initial diameter. That gives the lateral strain. Here it has been given delta D as 0.0079 mm divided by initial diameter of the bar is 12 mm. So if you take the ratio, you are going to get the lateral strain like this. And linear strain we have calculated already. Linear strain is delta L by L. That is along the length. Linear strain is along the length. So that we have calculated 2 into 10 power minus 3. Take the ratio. So this is the value of mu. Mu has no units. It is just a number 0.329. So that is the value of Young's modulus. Next, once you know these two, E and mu, using the relationship between the elastic constants, you can find out the other two constants. So since you know E and mu, you can use this relation. E is equal to 2G into 1 plus mu. So to get the value of G. So G you are going to get after substituting for mu and E. So E is this value, mu is this value. If you substitute that and simplify, you will get G as 33,265.6 Newton per mm square. Units you should be very careful. So this relationship you should be knowing. Next, once you know E and mu, you can find out the value of K, bulk modulus of elasticity of that material of the rod by using this. E is equal to 3K into 1 minus 2 mu, or K is equal to E divided by 3 into 1 minus 2 mu. Once again, you substitute for E and mu, you will get the value of K like this. So the unit of K is also Newton per millimeter square. So this is a simple problem wherein he has given change in increase in length and decrease in diameter and force. They have given. He has asked the elastic constant. So what we have done is first we have calculated Young's modulus value by taking stress divided by strain. Stress is force divided by area. Strain is change in length divided by initial length. So using that ratio, you got E. Then ratio of lateral strain to linear strain, that is mu, Poisson's ratio. Lateral strain is delta D by D. Linear strain is delta L by L. So by using that formula, we can get the value of mu. Then using these two relations between the elastic constants, you can compute the value of G and K. So E, G, K, they have the units Newton per mm square. Mu doesn't have any unit. It's just a number. That is one problem. Next, second problem. See, a tensile bar of circular cross section tapers uniformly from 28 mm to 22 mm diameter in a length of 300 meters. So 300 mm. Please take this as 300 mm. An axial load of 70 kilonewton is applied and an extension of 0.5 mm is observed. Okay. Find Young's modulus. Find Young's modulus E value. If mu, Poisson's ratio is 0.3, find G and K. Find rigidity modulus and bulk modulus. So here mu is given. We have to find out the other three using this data. So it is a problem of tapering circular bar. We know the formula for elongation of a tapering or deformation of a tapering circular bar. So here the force is given as 70 kilonewton. See, axial load means it is tensile force. Here 70 kilonewton is the force. So and the diameter varies from 22 mm to 28 mm to 22 mm. So D1 is 28 mm, D2 is 22 mm. So I have not drawn the figure here. So you can refer the earlier notes for the figure. It's a tapering circular section. Okay, D1 is the diameter at one end, D2 is the diameter at the other end. So D1, D2 are 28 mm and 22 mm. P value is 70 kilonewton or 70 into 10 power 3 Newton. So and he has also length of the bar he has given 300 mm. So L value is 300 mm. Then extension of the bar observed is 0.5 mm. So 0.5 mm is the delta L value. Now you have to know, you should know this formula. So this formula we have derived. So this is the formula to find the elongation of a tapering circular bar when it is subjected to a tensile force. So 4PL divided by pi E d1 d2 is your delta L. So in this formula, E is unknown. All the values are known. So delta L is 0.5 mm, P is 70 into 10 power 3 Newton, L is 300 mm, D1 is 28 mm, D2 is 22 mm. If you substitute in that formula, you will get the Young's modulus value E as 86,811.78 Newton per mm square. Once again, it is not steel, it is some other material. So by knowing the value of E value, you can judge whether it's steel or not. So once you get the value of E, since mu is given, you can find the elastic constant G and K using the formula. Now the first formula is E is equal to 2G into 1 plus mu. So you know the value of E here. You know the value of mu as given value of mu as 0.3. So substitute in this, you will get G. So once again, G will be in Newton per mm square. Then bulk modulus, use the other equation. We know that E is equal to 3K into 1 minus 2 mu, or K is equal to E divided by 3 into 1 minus 2 mu. Substitute for E and mu and simplify, you will get the value of bulk modulus of velocity K as this much. So this is the simple problem only, but you should be knowing the respective formula, which formula we have to use, and also the units are very, very important. So all the values, you try to convert it into Newton and mm. Then you substitute in the formula. See the next problem. A bar of 20 mm diameter and length 200 mm extends by a length 0.4 mm upon application of a load P. So P is unknown here. Load is unknown. Tensile load. Because it has given extends. The bar is extending means it is tensile force P, which is unknown here. What is the value of P if E is equal to 2 into 10 power 5 MPa? MPa is nothing but Newton per mm square, megapascal. So it is steel. So steel material. What is the change in cross-sectional area of the bar at this stage if mu is equal to 0.28? So mu value he has given 0.28. I have told you that for steel, mu value can vary from 0.25 to 0.3. Here he has given it as 0.28. So this second stage. So first step, we have to calculate the load P. Then after finding load P, suppose if mu is equal to 0.28, what is the value of change in cross-sectional area? That is second step. Next, third, there are three questions in this problem. If the extension of the bar were to be limited to 0.3 mm, extension of the bar means it is delta L. If delta L is to be limited, if delta L is 0.3 mm under the same load P, so whatever load P we have calculated, under the same load, if at all you want to have the same extension, what should be the diameter of the bar? See, understand this problem. So these types of problems are important. Don't expect direct substitution problems. So here there are three stages in the problem. In the first stage, we have to find out the unknown tensile force P. In the second stage, we have to find out the change in the cross-sectional area of the bar. In the third stage, if the extension is restricted, what is the corresponding diameter of the bar? So P is unknown. Change in cross-sectional area, that is delta A. We can call it as delta A. Delta A is unknown. That is initial cross-sectional area minus final cross-section area, or the difference between those two. Then third part, diameter of the bar is unknown if the if the extension is restricted. So let us take one by one. First, let us find out P. So he has given it is a uniform bar or a prismatic bar of diameter 20 mm. Simple formula to find deformation is delta L is equal to PL by AE. This is the first initial derivation we have done. So PL by AE, substitute. So here delta L is how much? Delta L is 0.4 mm. See here, extends by a length of 0.4 mm. So delta L is 0.4 mm. E value is 2 into 10 power 5. A value is diameter is 20 mm. So A is pi d square by 4. Pi into 20 square by 4 divided by L. So L is 200 mm. So length 200 mm he has given. So if you substitute this and simplify, you will get P value 125.6 kilonewton. Actually, if you simplify this, you will get the value in Newton. Okay, so you can put as it is, no problem. If you are in newtons, it will be 125,660. So much kilonewton you will Newton you will get. So this into 1000 will be the value in Newton. That's what you are going to get here. Okay, then that is the first part. So we have found out the tensile load to cause that much deformation. Next, second part, mu is given as 0.28. What is the change in the cross sectional area of the bar when P is this much? That means at that stage means your delta L is 0.4. So delta L is 0.4. So mu is given. So we have to find out the change in area. So for finding out the change in area, we need the change in diameter. Unless you know the change in diameter, you cannot find out the change in area. So for that, we have to use the formula of Poisson's ratio. So mu is equal to 0.28. Poisson's ratio mu is defined as lateral strain divided by linear strain. Lateral strain is delta D by D for a circular bar, divided by linear strain is delta L by L. Now, in this formula, you can see that everything is known except delta D. If you find out the expression for delta D, if you simplify this, delta D will be this much. Mu into delta L into D divided by L. Just simplify this. Delta D is the unknown here. Change in diameter is the unknown. Substitute now. Mu is 0.28, delta L is 0.4, L is 200 mm, D is 20 mm. If you simplify this, you will get the change in diameter as 0.0112 mm. So this will be in mm. If you simplify this, you will get 0.0112 mm. Actually, when the bar is elongated, length will increase, diameter will reduce. So here this is actually D1 minus D2. So D1 is initial diameter, D2 is the final diameter. Now the change in diameter is this much. Therefore, what happens? The final diameter D2 will be initial diameter is 20 mm minus this. So that gives your final diameter D2. Here I have taken D1 as the initial diameter, D2 as the final diameter. So change in diameter is D1 minus D2, which is equal to this. D1 is 20 mm. D2 will become now 19.9888 mm. So you have to take some 3-4 digits after decimals because it's a very small number. So one thing you should keep it in mind, when the number is very, very small, you have to take more number of decimal places. So for example, 0.0112. See, 4 digits are there. Here also we have to take for 4 digits because the values will vary much. So when the number is very, very small, take to 4 or 5 digits of decimal. Anyway, using calculator we can do all those things. Now this is the final diameter. Once you know the final diameter, you can calculate the final area. So when D2 is this much, A2 is the final area after extension. So pi D2 square by 4, which is this much. It is in millimeter square. 313.81 mm square. This is mm square. So square is missing here. You can take that. Now what is the change in area? Change in area is delta A. Initial area minus final area. So initial area is pi into 20 square by 4 minus final area is this one, 313.81. If you simplify that, you will get the change in area. So simple. The only thing is you have to understand the concept. So when length increases, diameter reduces. When diameter reduces, area reduces. So initial area minus final area. So is this much. That is your change in area. Next, third one. The third part of the problem is, suppose if the elongation is restricted to 0.3 mm of that bar. Elongation of that bar is restricted to 0.3 mm. That means delta L is equal to 0.3 mm. What is the corresponding diameter of the bar? D value we have to find out. So for that, what you have to do is here. So delta L is given as 0.3 mm. P is 125.6, whatever we have calculated, kilonewton. So what should be the, what is the diameter of the bar? So for that, once again, you have to use the same formula. Delta L is equal to PL by AE. So here A I have replaced it as pi d square by 4. That's all. Now in this D is unknown. So if you substitute everything and simplify, you will get the diameter as 23.09 millimeter. So P we have to take 125.66 into 10 cube because it should be in Newton. L is 200 mm. 4 is a constant. Pi into delta L is 0.3 mm. E value 2 into 10 power 5. So all the things we have to substitute. Then D you can find out. So this is the diameter. The 23.09 mm is the diameter of the rod. If at all the extension of the bar is restricted to zero point 0.3 mm. See, it's an important type of problem. All the three steps are there. First step, force is unknown. All the other things are given. Second step, mu is given. Change in diameter and change in area of the bar is calculated. Next, third step, delta L is restricted. What is the diameter? What should be the diameter of the bar so that same 0.3 mm deformation, elongation takes place. That is the thing. So this is another important problem. So all same problems you try to work it out. So next problem I leave to you only. I will take fifth one. Fourth one you try to get it. I think fifth one also you can do. It is almost generalized Hooke's law we have used for doing this fifth problem. Anyway, it's a pressure only hydrostatic pressure problem. Don't hydrostatic pressure means, see, let me explain this problem. A 1 meter long prismatic bar with square section 30 mm side. So 30 mm by 1 meter length. So length is 1 meter. See here, length is 1 meter, but this one is 30 mm by 30 mm. So width is 30, thickness is also 30, depth is also 30. Is subject to hydrostatic pressure. So hydrostatic pressure means you have studied in fluid mechanics. Compressive force. It is a compressive force, hydrostatic force. Suppose if this block, prismatic bar is immersed in water, so pressure will be equal from all these sides. So that is your Pascal's law. You have studied in your FM. Hydrostatic law and Pascal's law are the very important laws in fluid mechanics. So it is subject to a equal hydrostatic pressure of 80 Newton per mm square or 80 MPa in all the directions. So here he has given E value 200 GPa. 200 GPa means 200 into 10 cube MPa or 2 into 10 power 5 MPa. Mu value is 0.3. Find the change in volume and bulk modulus of elasticity. See, this type. So here hydrostatic pressure means it is equal, but only thing is it is compression. Compressive stress, not tensile stress. Okay. So what? Suppose if it is immersed in water, pressure acts from all the three directions, and that pressure is 80 MPa. That is the mean. But same formula holds good. We have to apply generalized Hooke's law to find the strains. So let us take this along the length as x direction. This is y direction. This is z direction. Now I have used this is generalized Hooke's law. If you want Ex is the strain in x direction, which is given by, see, it is 80 MPa in this direction. So stress is 80 divided by E value is 2 into 10 power 5. So this is sigma by E. That's what. It is compression in x direction. That's why minus sign is used. Then coming to y direction, 80 MPa is compression in y direction. Therefore, it should be tension in x direction. So we have to take positive. Let's see here. In plus, mu will come into picture because it is lateral strain. Mu is given as 0.3 into same sigma, because sigma in y direction is also same. 80 divided by 2 into 10 power 5. Next, in z direction also, we have the same stress, that is 80 MPa. So stress means here pressure. So pressure is external effect, stress is internal effect. Values will be same. So here plus 0.3. So point plus, because in z direction also it is compression. The effect of that in x direction will be tension. So it is plus 0.3 into 80 divided by same. So if you simplify this, you will get Ex this much. In y and z direction also, you will get the same answer because the pressures are same, stresses are same in all the three directions. See what happens. So pressure is an external effect, stress is an internal effect. Numerically, they are equal. So that's why we are using the same equation. So once you get Ex, Ey, Ez, since the stress is same in all the three directions, so you are getting same value for Ex, Ey, Ez. So all you can see that they are all compressive. So the negative sign shows that there is a reduction in the volume due to this hydrostatic pressure. So EV is the volumetric strain. So volumetric strain EV is equal to the sum of all these three, Ex plus Ey plus Ez. If you add all these three, you'll get minus 4.8 into 10 power minus 4. So he has asked change in volume. We know that EV, volumetric strain, is equal to change in volume divided by original volume. So our change in volume delta V is equal to EV into V. Okay, so EV we have calculated, into V is nothing but the volume of the bar. Volume of the bar here is, volume of the prismatic bar is 1 meter. Cube bracket. Can you see the screen?
No, sir.
No. I think some connection it was temporarily lost. From 2 minutes, 2 minutes back, it was lost. Is it not? Now can you see?
Yes, sir.
Yeah. How many minutes you lost that connection? This problem I explained, you know. You understood this problem? This one? Was the connection there when I explained this problem? Can you hear me?
Yes, sir.
Can you see the
Yes, sir.
screen? Okay. This
Yes,
problem
sir.
you understood? This I explained, you know. This one, problem number 5. Generalized Hooke's law has been applied on this prismatic bar. Strains are equal. So then we have found out the volumetric strain and change in volume. Then after this, we have to get the elastic constants. That's what is asked. So K value he has asked. So E is equal to 3K into 1 minus 2 mu. So that you just substitute here. So K will be E divided by 3 into 1 minus 2 mu. So mu value is given as 0.3. So E value and mu value will be knowing. So just substitute and simplify, you will get the value of K. So this is what I wanted to explain. Next, the next problem is also problem on generalized Hooke's law, which I had explained. The sixth problem is similar to a problem which I have done earlier. You can go through that. Seventh one, see, let me take the seventh problem. Okay. All these are important. So seventh problem, what it says, a specimen of length 200 mm and 20 mm diameter is subject to a tensile force of 25 kilonewton. Length and dia of the specimen are found to change by 0.2 mm and 0.006 mm respectively. Find the elastic constants. So this problem is similar to the first problem. Problem number 1. He has given the force here. Initial length 200 mm and initial diameter 20 mm. Change in length or increase in length is 0.2 mm. Decrease in diameter is 0.006 mm. So he has given all these details. We have to find the elastic constants. So first we have to get the value of Young's modulus by calculating stress and strain. Stress is force divided by area. Strain is delta L by N. So we can calculate E value first. Then mu value, Poisson's ratio is the ratio of lateral strain to linear strain. Lateral strain is delta D by D. Linear strain is delta L by N. Okay. So that if you substitute, you will get mu value. Then using the formula of relationship between the elastic constants, you can find out the other two elastic constants G and K. So this type of problem, first problem resembles this seventh problem. So data is different, that's all. So you can go through that. Next, see this eighth one. A bar of rectangular section is subjected to tensile stresses sigma x, sigma y, sigma z along the XYZ directions respectively. Show that there is no change in the volume of the bar if the sum of these stresses is 0. So sigma x, sigma y, sigma z, they are the stresses acting in the three mutually perpendicular directions x, y, z. So what we have to prove is delta V will be 0 if the sum of these stresses is 0. So for that we have to use the generalized Hooke's law for writing the strains in the three directions Ex, Ey, Ez. So since all are tensile, so I have told you that in x direction if you are writing due to sigma x it is tension, due to sigma y and sigma z it will be compression in x direction. Even though they are tension in y and z direction, their effect in the other two directions will be compression. So that is why minus I have taken. And what then volumetric strain is EV, Ex plus Ey plus Ez. You just add all the three, try to get the common term. Common term here is sigma x plus sigma y plus sigma z. So that is the common term. So for that you can put it as 0. So what happens? So this what he has given is if this EV will be 0 if sigma x plus sigma y plus sigma z is 0. So if you put here sigma x plus sigma y plus sigma z as 0, you will be getting EV as 0. So then change in volume also will be 0. So that is the meaning. Okay. So it's a simple bookwork. From generalized Hooke's law, if the sum of all the three stresses are equal to 0, then there is no change in volume of that bar. That is the meaning. So today in this class what I have done, so two derivations I did. So relationship between E. See, first morning I explained about this. We have derived this equation. E is equal to 2G into 1 plus mu. That we derived in the morning. So this one. Now in this class, afternoon class, what we have done is we have derived this equation. E is equal to 3k into 1 minus 2 mu. And from the first two equations, by eliminating mu, you can get the third equation. This is the third equation. Okay, then we did some problems of finding elastic constants, different types of problems, given different data, how to find the elastic. Compressive stress problem, that also I explained. Then this is similar to the earlier problem which we have done in the last class, so you can go through that. So this is similar to first problem. Problem number 7 is similar to problem number 1. Data is different. And lastly, we have proved this. So this is what I wanted to explain you today. So in the next class, the last topic in this module is temperature stresses or thermal stresses. This I am going to explain in the next class. So this one along with the problems, numerical examples. So this temperature stresses, we have to study for both simple bars as well as compound bars. So both we have to cover. So this is a very big module, big chapter. So almost all I have covered. So if I do this, then everything will be over. All the derivations I have explained, you have to work. So only if you practice, then only you can get the idea. Otherwise, it is very difficult. Okay. So once you start reading, then you will be having some. You may develop some doubts. So later on we will discuss. So go through the notes, work out the same problems and derivations in a notebook of your own. Okay, let me take the attendance now. (19,003). (19,003). Ajay Kumar.
Sir. Yes, sir.
Yes. Darshan 005.
Present, sir.
006 Divyashri.
Present, sir.
007 Janavi.
Present, sir.
010 Padma.
Present, sir.
011
Present, sir. Present, sir.
ಏನು ಯಾರ್ದು ವಾಯ್ಸ್ ಇಲ್ಲಲ್ಲ.
Present, sir.
ಆಯ್ತು. ಮೇಧೇಶ್ 013.
Present, sir.
016 Srilakshmi.
Present, sir.
017 Shreyas.
Present, sir.
019 Shweta.
Present, sir.
021 Surya.
Yes, sir.
Okay, that's all I think. Now, how are you feeling this subject? Yes, who is that?
Assignment questions.
Assignment. ಕೊಡ್ತೀನಮ್ಮ. Assignment ಪ್ರಿಪೇರ್ ಮಾಡಿ ನಿಮಗೆ ವಾಟ್ಸಪ್ ಹಾಕ್ತೀನಿ ಆಯ್ತಾ?
Yes, sir.
ವಾಟ್ಸಪ್
Thank you,
ಗ್ರೂಪ್
sir.
ಹಾಕ್ತೀನಿ. ನಿಮ್ದು ಮೇಲ್ ಗ್ರೂಪ್ ಇದೆಯಾ? ಕಾಮನ್ ಮೇಲ್ ಐಡಿ ಇದೆಯಾ ನಿಮ್ದು? ಮಾಡಿದಾರಾ? ಕ್ರಿಯೇಟ್ ಮಾಡಿದಾರಾ ಮೇಲ್ ಐಡಿ 19 ಬ್ಯಾಚ್ಗೆ?
Yes,
Yes, sir.
It is there? Then I can mail also. ಅದನ್ನ ನಿಮ್ಗೆ ಕಳಿಸ್ತೀನಿ ನಾನು. ವರ್ಕ್ ಮಾಡಿ ನಿಮ್ಗೆ MSc 1 ಟೈಮ್ಗೆ ನೀವು ಸಬ್ಮಿಷನ್ ಮಾಡ್ಲಿಕ್ಕೆ ಆಗ್ತದೆ. ಫಸ್ಟ್ ಟೆಸ್ಟ್ ಟೈಮ್ಗೆ. ಓಕೆ. ಏನ್ ಅರ್ಥ ಆಗ್ತಾ ಇದೆಯಾ? ಏನ್ ಹೇಳ್ಬೇಕು ನೀವು? ನಾನು ಪಾಡ ಹೇಳ್ಕೊಂಡು ಹೋಗ್ತಾ ಇರ್ತೀನಿ. Are you understanding?
Yes, sir.
ಎಸ್ ಸರ್. ಕಾಲೇಜಿಗೆ ಬಂದಾಗ ಗೊತ್ತಾಗ್ತದೆ, ಅವಾಗ ಕ್ವಶನ್ ಕೇಳಿದಾಗ ಗೊತ್ತಾಗ್ತದೆ ಎಷ್ಟು ಮಟ್ಟಿಗೆ ಅರ್ಥ ಆಗಿದೆ. ಸ್ವಲ್ಪ ಸಬ್ಜೆಕ್ಟ್ ಇದಿದೆ ಆಯ್ತಾ, ನೀವು ಸ್ಟಡಿ ಮಾಡ್ಬೇಕು. ಡೌಟ್ಸ್ಗಳು ಬರೋಕ್ ಶುರು ಆಗ್ತದೆ ನಿಮ್ಗೆ. ಯಾಕಂದ್ರೆ ಇಲ್ಲಿದ್ರೆ ನಾವು ಡೈರೆಕ್ಟ್ ಆಗಿ ಬೋರ್ಡ್ ಮೇಲೆ ಬರ್ದೆಲ್ಲ ಕ್ಲೀನ್ ಆಗಿ ಎಕ್ಸ್ಪ್ಲೈನ್ ಮಾಡ್ಬೋದು. ಇದರಲ್ಲಿ ಕಂಪ್ಯೂಟರ್ ಮಾಡೋದು ನಿಮ್ಗೆ ಎಷ್ಟು ಮಟ್ಟಿಗೆ ಅರ್ಥ ಆಗ್ತದೆ ನಮಗೆ ಗೊತ್ತಾಗಲ್ಲ. ಸೊ ಹಾಗಾಗಿ ನೀವು ಸ್ವಲ್ಪ ಚೆನ್ನಾಗಿ ಓದ್ಕೊಳ್ಳಿ. ಕಾಲೇಜಿಗೆ ಬರುವಾಗ ಆದಾಗ ನೆಕ್ಸ್ಟ್ ಸ್ವಲ್ಪ ರಿವೈಸ್ ಮಾಡಿ ಕಂಟಿನ್ಯೂ ಮಾಡ್ತಾನೆ, ಆಯ್ತಾ? ವಾಟ್ ಸಬ್ಜೆಕ್ಟ್ ಇದು ಮತ್ತೆ ಫ್ಲೂಯಿಡ್ ಮೆಕ್ಯಾನಿಕ್ಸ್ ಎರಡು ಸ್ವಲ್ಪ ಕೇರ್ಫುಲ್ ಆಗಿ ಇದು ಮಾಡಿ, ಆಯ್ತಾ? ಬಿಕಾಸ್ ಬೋತ್ ದಿ ಸಬ್ಜೆಕ್ಟ್ಸ್ ಲಾಟ್ ಆಫ್ ಡೆರಿವೇಶನ್ಸ್, ಲಾಟ್ ಆಫ್ ನ್ಯೂಮರಿಕಲ್ ಎಕ್ಸಾಂಪಲ್ಸ್. ಎಕ್ಸಾಂಪಲ್ ಅದೇ ಬರೋದು. ಸೊ ನಿಮಗೆ ಓನ್ಲಿ 80% ಪ್ರಾಬ್ಲಮ್ಸೇ ಬರೋದು, 20% ಮಾತ್ರ ಡೆರಿವೇಶನ್ ಮತ್ತೆ ಥಿಯರಿ ಆ ತರ ಇರ್ತದೆ. 80% ನ್ಯೂಮರಿಕಲ್ಸೇ. ಔಟ್ ಆಫ್ 3 ಕ್ವಶನ್ಸ್ ಒಂದು ಡೆರಿವೇಶನ್ ಅಥವಾ ಥಿಯರಿ ಇರ್ತದೆ, ಇನ್ನೆರಡು ಪ್ರಾಬ್ಲಮ್ ಇರ್ತದೆ. ಔಟ್ ಆಫ್ 20 marks, ಇಫ್ ಯು ಹ್ಯಾವ್ ಗಾಟ್ 3 sub questions, 2 will be problems, 1 will be either derivation or some theory related, ಆಯ್ತಾ? So that's why, so you should be very careful. 80% problems. Okay. Have a nice day. So next class is on Monday. Okay. I will do temperature stresses. ಎಲ್ಲ ಓದ್ಕೊಳ್ಳಿ. ನಾಳೆ ನಾಡಿದೆಲ್ಲ ರಜಾ ಉಂಟಲ್ಲ, ಯಾವುದು ಟೈಮ್ ವೇಸ್ಟ್ ಮಾಡಬೇಡಿ. ಆಸ್ ಫಾರ್ ಆಸ್ ಪಾಸಿಬಲ್ ಟ್ರೈ ಟು ವರ್ಕ್ ಇಟ್ ಔಟ್. ಓಕೆ, ಥ್ಯಾಂಕ್ ಯು.
Thank you, sir. Thank you, sir. Thank you, sir.
ನಿಮ್ಮನ್ನೆಲ್ಲ ಯಾವಾಗ ನೋಡೋದು ಗೊತ್ತಿಲ್ಲ.
Thank you, sir.
ಥ್ಯಾಂಕ್ ಯು.
Thank you, sir.